Hi everyone, I'm Rock. Welcome to my animated algorithm channel, where we help you conquer your fear of coding interviews. Don't forget to like, subscribe, and save this video. Let's get started. Today, we're looking at a super classic problem called toSum. Here's the prompt. Given an array of integers nums and an integer target, you need to find the two integers in the array that add up exactly to the target and return their indices. Let's look at a concrete example together. Take the first test case provided by the problem. The array has the numbers 2, 7, 11, and 15, and the target value is 9. You can tell at a glance that 2 plus 7 equals exactly 9, right? Since the index of 2 in the array is 0 and the index of 7 is 1, we just return 0 and 1. The problem also very thoughtfully guarantees that each input will have exact. So, when we get this problem and need to find a combination in an array, what's the most intuitive brute force approach that comes to mind? It's definitely using a nested for loop to exhaust all possibilities. That means taking every number in the array and adding it to all the numbers after it, one by one, to see if they equal the target value. But obviously, the interviewer doesn't want to see this solution. Why? Because the time overhead of a nested loop is just too high. So the question is, how do we optimize it? Actually, if we shift our perspective a bit, we can cleverly use a hash map to trade space for time. Think about it. When we iterate to a number, let's say the current number is x, we don't really need to blindly keep searching forward. What we really need to find is whether the difference, which is the target minus x, has appeared before. Since we need to check if an element has appeared and also quickly grab its index, isn't that exactly what a hash map is best at? To make this easier to visualize, let's do a walkthrough using the array 3, 2, 4 with a target of 6. Picture this in your mind. On the left is the array we are iterating through, and on the right is a hash map that starts out completely empty. We're ready to start. First, our pointer arrives at index 0, and the current number is 3. We take our target value 6, subtract the current 3, and get a difference of 3. At this point, we turn to the hash map on the right to check, is there a 3 in there? No. Alright, so we take the current number 3 as a key and its index 0 as a value and store them in the hash map. Now the hash map has one record. Next, the pointer slides one spot to the right, arriving at index 1, and the current number is now 2. We take our target 6, subtract 2, and get a difference of 4. We check the hash map again. Is there a 4? Right now, the hash map only has a 3, number 4. That's okay. We go ahead and store the number 2 and its index 1 into the hash map. The hash map state is updated, and it now has 2 records. Then, the pointer keeps sliding to the right, arriving at index 2, and the current number is 4. Pay attention here, this is the key moment. We once again take our target 6, subtract 4, and get a difference of 2. We quickly check the hash map. Is there a 2? Yes, there is. The hash map tells us that the number 2 definitely appeared before, and its index at the time was 1. Awesome, this means we found it. We simply take the That walkthrough we just did is actually the core skeleton for writing our code. No matter what programming language you use, the core logic to implement this algorithm really comes down to just 3 steps. Step 1. Before you start iterating through the array, initialize an empty hash map or dictionary structure outside of it. The purpose of this hash map is to keep track of the numbers we've already seen and their corresponding indices. Step 2. Use a pointer or a loop variable to iterate through the entire array from start to finish. In every iteration, first calculate the target value minus the current number to get the difference we are eager to find. Step 3, and this is the most crucial step. Check if this difference exists in the hash map. If it does, it means we've found our perfect matching pair, and we directly return the index associated with that difference in the hash map, along with our current pointer's index. If it doesn't exist, we save the current number and its index as a key value pair in the hash map, and then continue iterating to the next number. As long as you get these 3 steps straight, writing the code becomes a piece of cake. Finally, let's analyze the complexity. Because we only need to iterate through the array completely at most once, and the time overhead for looking up values in the hash map each time is constant, while additionally only using one hash map to record the numbers we've searched, both the time complexity and space complexity of this algorithm are O(n). To sum it up, this is a fantastic foundational problem that classically demonstrates using a hash map to trade space for time, absolutely crushing the nested loop approach. Alright, that's it for today's problem. See you next time. Bye-bye.